So this very brief lecture is going to be on Python. It's just big O in general. It's basically how do we understand how efficient your algorithm is going to run. This is stuff that it would be nice to know for interviews. It's actually quite simple to memorize the different types of big O that's available to you. And then we're just going to go over this real quick. It may not make a ton of sense right now, but the overall theme that I want you to remember is every single time that you write some sort of program, it takes a little bit of time to run. You have to figure out how long it's going to take to run, pretty much. All right, so here's a couple of resources that I would recommend that you use. This is a visualization YouTube video of how long it takes to sort something. So as you can see right now, we've got 9 boxes, and each one of these bars is a certain length. And I want to go from the shortest length all the way up to the longest length. There are different types of sorting algorithms that are available to you. There's one called selection sort, shell sort. Remember we did bubble sort? Bubble sort is down here on the bottom left-hand corner. There is quick sort, which is when you do dot sort. In Python, when you just do dot sort, they're using a quick sort. What you'll notice is that each one of these pictures takes a different amount of time to actually start sorting these to go from smallest into largest. And this is just a visualization. You'll find very quickly that certain ones are going much faster, like shell sort is almost done. Quick sort finished first, shell sort, then heap merge sort, then heap sort. But what you'll notice is, oh my gosh, this bubble sort is taking forever because you have to do like a million pass-throughs. Remember, bubble sort is take a look at the first thing and the next thing next to it. If one is smaller than the other, flip it. Then move to the next one, then move to the next one, then move to the next one, and then do that over and over. You'll notice that almost every single sort is already finished except for bubble sort. And this, I'm not going to force you to watch it, but you can kind of see bubble sort is in dead last place right now. And it speeds up at the very end, but everything else was already finished. And the way that we're thinking about this is when I write the code, that's how long it's going to take to actually finish. So if I write really efficient code, then it's good to go. If I'm writing really bad code, it's not going to go that fast. Yeah.
So is there a chance that if we're using built-in methods that behind underneath the hood, so to speak, there's inefficiency that we're not aware of?
Sure.
Overall algorithm.
Sure. So the question was, when we do things like, let's say I have an array of like 1, 5, 2, 6, and I want to sort that, right? There are built-in methods into every language. There's a sort in Python, there's a sort in Ruby, there's a sort in JavaScript. Those sorts you can assume are going to be the fastest possible because it's built into the language. Underneath the hood, like somebody wrote dot sort, right? It doesn't just magically work. Someone wrote the code underneath the hood. And that code underneath the hood that's built into the core language is the most efficient algorithm that is available. So big O is a fancy way, this is the fancy definition, which is it's the complexity of your function, which is the O, in terms of input size. Nobody knows what that means. Let's actually take a look at some examples. From smallest to biggest, these are the rankings of big O. Let's say it's O of 1. You can give me, in terms of input size, like it doesn't matter how large the input is, the complexity of my algorithm is going to be the exact same thing. Then there's O log of n, which means 10 times the data takes 2x more than the time. O of n, which is a pretty common one, this is called linear time. 10 times the data means 10 times more time. And then you can continue to read this. This is inside of your curriculum for today. Let's take a look at some real life examples. So we've got O of 1 constant time. So the definition that I came up with is that the amount of time it takes to run your code is constant across the board. Whether you pass in one thing, whether you pass in a million things, it's the same thing. Let's take a look. So I've got this function called def first element is red, and you pass in an array of elements. Return true if the first element is red, otherwise return false. Does it matter how many things you pass in? No. You can pass me an array of 5 items, and I'm only looking at the first one. You can send me an array of 1 million items, and it doesn't matter how large that is, I'm still looking at the first one. It's a constant amount of time. to look something up. So a real life example. There was a village, you can look this one up if you want to. There was a village in Africa that said, our internet, we just got internet, but it's so slow that it's completely unusable. And to demonstrate this, what they did was they had, who's kicking me off? And this is, to demonstrate this, what they said was, we're going to put a gigabyte of data into this USB drive, attach it to a carrier pigeon, and send it to a town 50 miles over. And at the same time that the pigeon takes off, we're going to upload a gigabyte worth of stuff and try to send it to the same town 50 miles over. Obviously, based on the setup to the story, we know that the pigeon did in fact win, but it's not actually an accurate representation. Why?
Because the pigeon only carried it with one packet, whereas the spectrum has a lot of smaller packets that have access to some of the data before.
Sure. Yeah. So the thing with the carrier pigeon is that a USB drive doesn't get any heavier. You can put 1 gig of stuff on there. You can put 1,000,000 gigs if the USB drive supports that, but it's going to be a constant amount of weight. So the carrier pigeon flying from one town to another town 50 miles over, it doesn't matter how much data is actually put inside that USB drive because it's the same weight. It doesn't matter. Internet speeds, on the other hand, follow something called O of n, which is linear time. The more stuff that you upload, the longer it's going to take, right? Pretty much. So linear time is another one that you need to memorize. The first one is constant time, which is, it's going to be constant. Like it's a quick lookup. When you do like 1 + 1 on your machine, it's so fast that the computer just recognizes it as constant time. It's basically negligible. When we talk about O of n, we're talking about what's called linear time, which means that it's going to take a longer time to run based on the amount of stuff that you pass in. So let's take a look at this code. I have a method called does it contain it. Takes in 2 arguments. The first one is an array of values, and the second one is the value that you're looking for, this linear search, in case you haven't realized. I'm iterating over every single item inside the array, and basically I'm saying, if the item is equal to the value, return true, and if this whole thing runs these 3 lines over here, and it doesn't execute, then return false. So a real life example is I pass in 1, 2, 3, 4, 5, and I tell you to find the value of 5. Is it in there? It'll go, does 1 equal 5? No. Does 2 equal 5? No. 3 equal 5, 4 equal 5, does 5 equal 5? And finally, it returns true over here. Now, if I pass in an array of 5 things, it's really fast. What happens if I pass in an array of 1,000,000 things, and this value is the last thing in the array? It has to go through it 1,000,000 times. Even worse, what if I pass in 2,000,000 things, and the value's not even in there? Then I have to go through all 2,000,000 records. And that's what you're kind of thinking about. That's the worst case scenario, right? And it may not matter very much right now because the inputs that you're dealing with are only like 10 in size, so it's really, really small. But per day, if you're talking about something as large as Twitter or like Amazon or something like that, the number of records that they actually have to go through are quite large. So if you write an inefficient algorithm, then it's going to affect all these records all at the same time. It's going to take your computer that much longer to go through everything. The real life example is more money, more problems. Generally speaking, if you don't have a lot of money, then there are different problems if you don't have any money. But as you get, let's imagine that you are, like today, I don't have a ton of money. Like I'm just a regular person, right? I don't have a ton of money and I don't have a ton of problems as a result. But let's pretend I'm a billionaire. All of a sudden I've got $1 billion. I won the lottery overnight. I got to hire probably private security. I got to hire a lawyer. I got to hire like money managers to try to like protect my money from the government. Like I have to hire all these different things. Like, so the more money that you get, stereotypically speaking, the more help that you have to receive, the more things you have to look out for. People are going to come out of the woodwork looking for money. So that's the way that I think about O of n linear time. So the big 3 that you need to memorize: constant time, O of 1, linear time, O of n, and quadratic time, which is O of n squared. This is when you have, generally speaking, a loop within a loop. Let's take a look at this. We've got def all combinations that takes in an array of values. Let's say it's 1, 2, 3. I want to find every single, or let's say that I have, yeah, like I have 1, 2, 3 as an array, and I want to figure out every single possible combination of pairings that I can have with those numbers, which is 1, 1, 1, 2, 1, 3, 2, 3, and 3, 3. I have a results. I have a results array over here, and I'm going to iterate for number 1 an array, and then for number 2 an array, I'm going to append number 1 and number 2. Imagine I changed it to be like I have 3 names. I've got Marcus, I've got John, and I've got Dan, and I want to figure out every single possible combination of pairing partners that I can make. So it'd be like Marcus pairs with himself, then Marcus pairs with John, then Marcus pairs with Dan, and then John pairs by himself, then John pairs with Dan, and then Dan pairs by himself, and then how many times did I run through that algorithm? What's that? Roughly n squared.
Order of magnitude.
Yeah. So based on your input, the number of times it will take to run will double. I don't have a good example for this, other than just code. So O of 1, constant time. Let me just review this real quick. O of 1. What is O of 1, Justin?
That is linear, correct?
Nope. O of 1.
O of 1.
1 is a constant. Yeah. Because it's something that you know, so it's constant time. Can you give me an example of what constant time means?
As it is, right? Like, it's there, right?
Yeah.
It's persistent, pretty much.
Yeah, it is persistent. It's basically like, it doesn't matter. You can pass me one thing, you can pass me a million things. It's going to take the same amount of time. It's always going to be the exact same amount of time to run something. What about O of n squared? Let's go with Ethan.
Order n squared to be quadratic. An example that might be you have a grid and you want the x and the y coordinate of a specific value. You have to query through the whole grid, go the x direction and then y direction until you find the square.
That is pretty good, yeah. So O of n squared is quadratic time, meaning that let's say that I want to, if I have to do something like a loop within a loop and I want to print everything, I have 5 items and I want to print out every combination, I'm actually going to run through it 25 times because I have to run through the loop the first time and then run through the loop the second time, just like this. So number 1 is 1 the first time through, and then within the 1 for loop, I have to run through this 1, 2, 3, 4, 5 times. So I'm actually running through this 25 times. That's where the n squared comes from. And Ethan was saying that it's kind of like if I was doing a XY plot, I have to go through every single X number and every single Y number to try to find it. Right?
Or say you had a Sudoku grid and you're like, finding which value, which square in your Sudoku grid has a specific value.
Yep. Fair. That's fair. And then let's talk about O of n time, John.
O of n,
Mm-hmm.
and for the amount of input that or the time it takes to operate depends on it's directly correlated to the amount of input.
Okay.
If you're just searching like linear search example, you need to find a value in the array. The larger the array,
The longer
it's going
it'll
to take that much
Yeah.
time.
So I've been watching Designated Survivor on Netflix recently, and let's say that I only have stuff for O of n squared, O of 1 and O of n. I don't have n squared. So let's say that you want to meet the president, and that you want to find the most qualified person to meet the candidate out of a line of people, right? O of 1 is basically saying I'm taking the first person. So you can have a line as long as you want to meet the president. I'm just taking the first person. That person's going to meet the president, and that's it. Or American Idol. Like all the people line up on the sidewalk to try to go sing for the judges and stuff like that, right? So if they're like, okay, we need to find the next American Idol, and imagine that they just said, I'm just going to take the first person, and that's the American Idol. Like that's the person that we're going to test today. That's O of 1 time because it doesn't matter how long your line is. I'm just taking a certain person, or I'm just going to take the 5th person, or I'm just going to take the 24th person in line. That's O of 1 lookup. O of n, let's say that you're trying to meet the president, and like, if you get there early, you're going to get serviced early. If you get there real late, you're going to be the last one in line. And it's going to take that much longer because the line is just going to get progressively longer to try to meet the president. This is a bad example, but I hope you get the idea. Here are some key takeaways. When we talk about searches, Like we were showing that visualization at the very beginning with the YouTube video. If you are looking through an array, it's going to take a little bit longer. Why do you think it's going to take a little bit longer?
Because you're gonna go through each value, right?
You do have to go through each individual value.
Order, in an order which doesn't correlate with the data content.
Correct, yeah. So arrays are index based, meaning that I don't know if I showed you this picture. Let's take a look. A pillbox. I like to think of arrays kind of like these pillboxes. My grandmother has these, to memorize which pills to take on which day. And basically, these are by index, right? So Sunday might have, just the heartburn medication and the cholesterol medication. This might have hyperthyroid on Mondays and other medications on different days. But once you seal the top, it's kind of locked in there forever in an ideal world. And then you drop it, hopefully it doesn't open. So it's kind of like saying the 0th index contains all of these pills. The first index contains all these pills. The second index contains all of these pills. And that's the way that I kind of envision arrays as well. Certain indexes hold specific values. When you search through an array, it has to keep track of two things. One of them is the index of which number it is, and then the other one is the value of what's actually at that particular index. It takes a little bit longer to search through arrays because you have to keep track of that second bit of information. If you were to look through a hash, it's actually a little bit faster to search through because you have to have the key in order to look up the value. So imagine this. A real life example of this one is VIN numbers for cars are actually not stored with ID numbers, like in an auto increment. Like it's not 1, 2, 3. Like the first car in the database is this particular VIN number, which is this make, model, and it belongs to this user. It's not like that. The way that they actually store the data for VIN numbers is they just have the specific VIN number, and that points to a car, because a VIN number is always going to be unique. So instead of saying, number 1, is this one this VIN number? Number 2, is this VIN number? Like that's an O of N lookup because that's a linear time lookup. But if you have the exact key that you're looking for, it's like I'm looking for VIN number 4L7T. That one they can find immediately inside of a hash because there's a unique key to put it up there.
So the key in a hash is correlated to the memory address?
Yes.
Okay.
Yes, and I will talk more about memory address and basic computer science stuff at a later time. I think it's during week 10 or week 11. So, or I can do it sooner. It's up to you. But I have scheduled it for week 10. So we'll talk about memory addresses and like how hashes and how arrays work. These are just some things to memorize. I just want you to have this in your mind, but we're not really going to be practicing this that much. Yeah. So arrays searching is really slow, or hash searching is really fast. Avoid nested loops, which are loops within loops. And I know that everyone does that during the first week. And then if you find something, if you find yourself writing code that's like loops within loops, or the worst I've seen is a loop within a loop within a loop, so 3 levels deep of loops, you might want to refactor that. Because even if you were to run one loop and then run another loop and then run another loop, that's 3 O of N versus O of N to the, I don't even know what that is, right?
Ordering would be 1,000 times slower.
I'm going to look at someone's code from the very first week, and we can try to evaluate over like the next 2 or 3 minutes, more or less what the big O notation is. I'm going to choose this random day, Thursday. I'm going to choose this random credit check. And I'm going to choose, I don't know who this is, so I'm going to just grab it. Okay.
I knew it.
All right, so we'll do a quick review. So credit check, if you remember, was the Loon algorithm, which is basically I'm going to reverse the numbers. I'm going to take every other digit, which is the 4, the 5, the 7, the 2, and so on and so forth. I'm going to double that. If it's over 10, then I'm going to add them together. And then I add all the numbers together. If it's evenly divisible by 10, then you know it's a legitimate credit card number. I'm really not going to look at whether or not he solved it correctly. I'm just going to look at a few things. One is going to be syntax, and then the other one is going to be whether or not, like, what the big O notation is. Okay. Okay, let's take a look at this. Let multiplied array equal array.reverse. What do you think is happening with the reverse? Obviously, reverse is built in, right? So if I have 1, 2, 3, 4, 5, and I call it reverse on it, it goes 5, 4, 3, 2, 1.
It's taking just keeps adding it. Actually, I take the first one.
Yeah, it's taking the first one, it's putting it to the last. Then I keep moving it until I reach the last thing. What do you think? What do you think the big O notation on that one is? So I've got just 1, 2, 3, 4, 5, and eventually I'm going to get 5, 4, 3, 2, 1. But a bunch of calculations have to happen in the meantime, right? Maybe underneath the hood they have an empty array, and they say, okay, starting from the back, I'm going to repopulate it. So I'm going to go 5, 4, 3, 2, 1. I'm going to start populating from the last thing. What do you think it is? Probably an O of n. Yeah, that makes sense to me. So already we know that this line of code to begin with is already O of n because of the reverse here. After you reverse it, which is O of n, I'm going to map. What does map mean?
Make a second array.
I'm going to make a second array. I'm going to pass through the original array that I just created, right? So if I am going to map over an array, that means I'm iterating over the array, which is what? O of n. So this line of code already is how many is what would you calculate the big O notation to be? 2? Yep, 2 O of n. Yep. So this is roughly what it is right now. When you have the 2 in the front, you generally, it's a fancy way of saying it, drop the coefficient. Because if I have, basically as this number gets larger, if you multiply by 2, it's pretty much negligible. Let's say I have $100 billion, and then I multiply my wealth by 2. Now I have $200 billion. Am I still a rich person?
Yeah.
Yeah, so that's generally the idea here. So I'm going to drop this. So this first line of code is O of n. Let's add a single comment. Okay. Everything looks good in terms of syntax. I like it. Okay. Let's look at the second line of code. First thing I'll notice is you need a space. So it's going to be if index mod 2 is equal to, you can actually triple equal. So that's the syntax issue that I'm finding here. What do you think this is? If index mod 2 is equal to 0,
Constant.
it's going to be a constant time. Any sort of mathematical operation, if I do, like again, computers are so fast, right? So you can have any amount of mathematical computations in here, and it doesn't matter. It won't affect the overall runtime of the code. So any sort of math, it's just going to be O of 1. Return digit, O of 1. It just says return something, just do something. So there's O of 1, else return digit times 2. Any sort of mathematical operation is O of 1. And generally what I'll do is I'll just kind of keep track of the largest thing so far. So since O of n is larger than O of 1, I just hold on to O of n. That's the overall runtime so far. And then return multiplied array.reverse. There's another O of n. So this whole thing is going to be O of n. So O of n. This is O of 1. This is also O of 1. So this is also O of n. So if I were to add it, it's O of n plus O of 1 plus O of 1 plus O of n. So it's plus 2 O of 1 plus O of n, which is equal to 2 O of n plus 2 O of 1. You drop the coefficients, so it now becomes O of n plus O of 1. And you take the larger of the two. So the whole runtime of this particular algorithm so far is just going to be O of n. Again, this is not something that you need to know. Just like I don't expect people to be able to do what I just did. Just kind of keep track that all the code that you do write does take a bit of time to run. You need to be able to determine how long it takes to run. Okay, I have 6 minutes to go over.